All right, so if I got that, okay, so I'm going to try to solve for n, right? So I need, and I don't know when I first look at this, but when they give me a question that is a literal equation like this, and I have to solve for a variable, the idea is to try my hardest to isolate that variable, right? In the hopes that that variable is a first degree variable. If not, then we'll get into working with variables of second degree inside literal equations, which is really what's going to happen here. But don't you multiply both sides by 9? So I get 9s. Right, so if I rewrite it this way or leave it this way, I cannot isolate just one n, right? Okay, so I do need to multiply that through. And I apologize that my s sometimes might look like a 5, but we'll try to keep it straight. So n squared plus n, right? So now I cannot isolate just this n, okay? Because what we want to do is we want to solve for n, okay? When you solve for n, and we talked about that, you should have talked about this in algebra. When you solve for n or solve for any variable, that means it's going to be written in terms of other things and not itself. Does that make sense? Okay, it'd be like writing a definition, but using the vocabulary word inside the definition. We talked in geometry that that's like a loop, right? It's a cycle that you can't get out of. So if I solve for n, but n is on the other side of the equation, that's kind of an infinite loop. That's a problem. So we will isolate or not isolate, but we will get everything equal to 0 since we have something squared. So now we can think about, okay, well, what two numbers multiply together give me 9s, but add up to n? That makes no sense, right? Okay, because we don't know what s and n are. So what is my only option? Quadratic formula, right? So when I'm solving my quadratic formula, remember it's always x equals whatever, right? But x was the variable when we talked about ax squared plus bx plus c equals 0. Here, the variable is n. So we're going to say n is equal to, okay? Now it's going to be the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to plug those things in. Now what is what is b? 1. So I'm going to have negative 1, okay, plus or minus. Now b squared would be 1 again, minus then 4a is 1, and now c is negative 9s. It's a constant. I just don't know what it is because s is undefined at the moment. But it will be a constant. It will be my c. Divided by 2a, which is 2, right? Okay, so now continuing through there then, I'm going to have, just simplifying, so this is n is equal to negative 1 plus or minus 1. Okay, so this is going to be what? Plus 36s all over 2. Okay. Now, if you type that in, that's your answer, and it'll accept that. Okay, but look at my feedback if I'm wrong. My feedback doesn't look like anything correct when I'm wrong. Does that make sense? So let's talk about how we can generate those. And it's just because there's a different... Yeah. So when I write it this way, I get negative 1/2 plus or minus 1 plus 36s all over 2, right? All they're doing is they're factoring out the 1/2, and they leave that then as it'd be what, negative 1 plus or minus 1 plus 36s. Now, that still doesn't look like what they gave us in feedback because they used the commutative property to put the plus or minus 1 or square root of 1 plus 36s in front, which I am against doing that because of the way we write things by hand, and they put the minus 1 in the back. I'm against that technique because if I'm writing it by hand, some people get sloppy and they don't know if that minus 1 should be under the radical or if it's outside the radical. Yes? Because it's the, so B is always going to be your coefficient of your middle term. So that's my A value, that's my B value, and that's my C value. So 1 squared is 1. Yes. I should give you the answer. Somewhere you should be able to see, like if I go to, and this is the thing, I'm not 100% sure if I can actually see the student view on my end of things. Let's see if I can. Yeah, so section 2, 1 to 4. So you should be able to see, so here on question 7, if you click on this plus sign, shows you that information. There should be, maybe you guys can't see it, but I can. When we're done, or when you come to me and ask, does anybody care if I pull up one of theirs real quick? Okay. Did you do number 7? If we have time towards the end of the period, we'll go back to question 15 and start working it out. But if not, we'll definitely do that first thing on Monday. This example here, so all I want to do is work through some of these questions with the quadratic formula. My hope is that it's not something that's extremely taxing and takes very long for us to do. If at any time, guys, if I have a preconceived idea of our abilities, and if I overestimate those abilities and just fly through something and we're all stuck or somebody's stuck, confused about something, slow me down, tell me to go back. Does that make sense? Okay. My preconceived ideas go off of what I've learned from you in geometry, and what I know in Algebra 1, Algebra 2 students should know when they get here. If those are incorrect notions, then I only know that once you communicate that to me. Does that make sense? And one way that you communicate that to me is through homework and through tests and quizzes, but I hope that you don't wait till a test or quiz to communicate that to me, because by then it's too late, right? Okay. So let's go ahead and plug away at this one. We got, if I try the GCF, try to pull a GCF out of this thing, that's not going to work. If I try the AC method, I'm going to get -3 as the product, and let's say, okay, what numbers multiply together give me -3, and I have to give me -5. None of those work. Okay, so then I default to the quadratic formula. Okay, or you could complete a square, but we said yesterday they're the same thing, right? In quadratic formula, a little bit easier. So we're going to say x is equal to the opposite of b plus or minus b squared minus 4ac all over 2a. The number one issue I have with students, and it happens every year, is there's going to be a handful of us that struggle with that set of order of operations for the discriminant. Okay, so just be careful there. Okay, if you're a person that continually gets that wrong, one, figure out why. But if you're on a test or a quiz, you know you've had failures with that in the past, maybe you use Desmos to guarantee that you've got the right values. Does that make sense? I'll talk about that here in a moment. But this is my A value, this is my B value, this is my C value, right? Now, when you take those values, my A value is 3, my B value is -5, and my C value is -1. Okay, a lot of people just take 3, 5, and 1, and that obviously would give you the wrong answer. So plugging stuff in, x equals opposite of b, 5, right? Plus or minus, what would be 5 squared then? -4, a is 3, and then c is -1. And then 2a is 6. Now my suggestion to you, and some of you will be fine with this, but my suggestion is to be deliberate when you're writing this stuff down here. Okay? Some people do that in their head and get it right. Some people do it in their head and never get it right. So just, I think, be deliberate. It's going to make things a little bit easier. Order of operations says you need to do this multiplication first, right? What's negative 4 times 3? Negative 12. What's negative 12 times negative 1? Positive 12, right? So what's 25 plus 12 then? 37. So that's where I'm going to get 5 plus or minus root 37 all over 6. Okay? And those are my two solutions. And I know it's a pain in the butt, and there's nothing I can do about it. But when you type it into WebAssign, you have to type that in once, and you got to go comma, and type that in a second time. And I think yesterday I talked about using cut and paste, Control V, Control C, or Control C, Control V to cut and paste those. You can also, I mean, there's different versions. I can go write 5/6 plus radical 37 over 6. That's the same thing as this first one, right? Okay. It will accept that. Okay. WebAssign does a good job of accepting alternate versions, much better than what Math Excel was programmed to accept when we were using that. Is that all right with everybody? Okay. Just something we talked about in the last class. If we factored something, let's say we factored something, we got like x equals 8 and x equals, I think one of them we did earlier was like negative 3. That thing came from x minus 8, didn't it? That thing came from x plus 3, didn't it? Okay. So once I got my solutions, I can figure out what the factors were that came from them, right? Well, if these are my solutions, then a factor would have been x minus that amount. Does that make sense? And x minus that amount. Now, if I FOIL that, I don't get back to what I started with. Okay? Because think about FOILing. You get x times x gives you x squared, right? What do we need to get? 3x squared. So there was a factor of 3 somewhere that we needed to bring back in. But that would be then the fully factored form of the left-hand side if for any reason we ever needed that. Yeah. Because if I would have done, think about, because it's the way we work backwards. If I'm at x, so this is positive 8, right? So it's always x minus that number. Here, it's x minus negative 3. It's always x minus whatever the solution is. And if I go x minus negative 3, what's that turn into? The x plus 3. Does that make sense? So whenever you have your solutions, it's always x minus whatever that solution is. X. Say it again. This one? No, because it's because this is the solution. That's the x-intercept. That's the x-intercept, right? And that's where I cross the x-axis. Then the factor is always x minus whatever that was. And it'll be a function. It'll be something we talk about in functions. So it'll make more sense when we get there. Right now you're not going to need it, but it is always x minus the x-intercepts. Okay. When we talk about it in functions, we'll just call that the x-intercept. We'll call it c. And we'll say if you know that x equals c is a root, then x minus c is a factor. And it's a theorem. Let's do this one. What's A? 4B, 12C, 9. Okay. So then I'm just going to run that stuff through my formula. So we're opposite of B, so negative 12. Plus or minus 12 squared, which is 144, minus 4, A was 4, so there's 16, right? Times C, which is 9. Anybody know what 16 times 9 is? 144 over 2A, which is 8. So what that gives me is negative 12 plus or minus root 0, which the square root of 0 is 0. All over 8. Now, you're not going to ever probably write it this way, but I'm going to do this. I'm going to write x minus 12, or x equals negative 12, plus 0 over 8, and negative 12, terrible negative sign, negative 12 minus 0 over 8. Do those both give me negative 3/2? Okay. Now, generally speaking, most people are going to say, okay, this plus or minus 0, they're going to say, well, I'm just not even going to write that again. It's negative 12 over 8. And you get one solution, right? And that's fine. That's what we get here. But in parabolas, if you get one solution, does anybody remember what one solution looked like graphically? Tangent. So at negative 3/2, my graph is going to just touch the x-axis one time. The fact that I get a double root here, when I do it this way, when I get a number as a solution to repeat itself, that is the algebraic kind of identifier that we are going to be tangent. And if we graph this thing, what was it, 4x squared? Was it plus 4x? Plus 12x? You see then at A, negative 1/2, or negative 1.5 or negative 3/2 comes here, and you're just touching there, right? We're just tangent to that point. Okay? What's the y-intercept of this graph? 9. How does that relate to, that's the c value. Okay? And that's something we'll talk about in great detail coming up as well. What you're going to find out is that, like, the first section of functions, which is chapter 2, you're going to think, man, we already did a lot of this in chapter 1. Chapter 1 is talking about solving equations, functions, a little bit different, but they're still quadratics. So there's going to be connections that are very similar. So I think maybe it's important to talk about those now as well. Okay, so let's do this last one real quick. What's A here? A is 1. What's B? 2. What's C? All right, so x is equal to the opposite of B, so negative 2, plus or minus B squared minus 4A times C, all over 2A, right? So what's 4 minus 4 times 1 times 2? Negative 4. Okay, so you have 4 minus 8 up here, right? So what's the issue there? Negative. Okay, so what do I do with a negative underneath a radical? You bring it out as an I. Okay, and that would leave you with radical 4, right? Okay, does anybody know who invented I? Nope. Leonard Euler. Okay. We're talking about Euler a little bit in geometry, but we'll talk. There's a lot of things that he's one of the, if we're listing like the top 5 mathematicians, he's going to be one of them. So negative 2 plus this plus or minus this becomes 2i, right? All over 2. And because, and this is the logic here. Some people start canceling things and aren't certain why they cancel things. In this situation, I can go blank, 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 right? And get negative 1 plus or minus 1i, and that's my answer. Okay? Anybody know why I can do that? That's not necessarily the answer. We can rewrite it that way, right? Do these two cancel then? Do these two cancel? Okay. So what if I had something as like, let's go 3 plus or minus 6 radical 2 all over 2. Can I just cancel there and put a 3 there and say 3 plus or minus 3 radical 2? Does that work? If I rewrite this as 3 over 2 plus or minus 6 radical 2 over 2, I can cancel here, right? And that does give me 3. But it's 3 halves plus 3 radical 2. Is that different than 3 plus 3 radical 2? As I would have gotten here if I just cancel that and that? Okay, so this is the correct way of doing it. You cannot do it that way. The only way that you can start, when you write, because basically what you're doing is you're writing 2 fractions as 1, right? Okay. You can only cancel if they all share a common factor. Okay. You can't just cancel the ones that do. They all have to share it. And to realize that, guys, I think it's easier. It's best to separate them into their individual fractions and then see if each individual fraction does cancel. And that's what we got here. So Leonard Euler came up with that stuff. I is your imaginary numbers, right? Okay, so does that mean they're fake? They're imaginary. Okay, so they're legit things. Maybe the name for them isn't all the greatest, but Leonard Euler came up with this stuff. And when he was coming up with it, it wasn't really until after he died that it became something that is really attributed to him, because he was working on his stuff and he died. But what happened then is that people like reading his work, and what he did, you guys ever go to a restaurant and they've got that little like wooden block with a spike coming out of it, and the server will take your receipt and put it on top of that? Okay, so that bottom receipt is the first order of the day, right? Okay, well, that's what he was, when he would work on his math, when he was done with whatever his paper was, like his parchment or whatever, he would set it on one of those things. Okay, so when they took all that stuff off and were trying to go through his work when he was when he had died, when they were cleaning out his estate and that kind of stuff, people were reading his work and like it was all backwards because the bottom was actually the first page, right? So it wasn't making sense to them. It wasn't until years later that somebody said, let's reorganize and look at this stuff, and basically we realized what he was talking about. But his main goal, now the idea, it wasn't really, he wasn't really working on this equation. His work was showing that he was actually trying to solve a cubic equation. But if I look at that equation, this is the purpose of I. Okay, because we should be able to solve every single quadratic equation, but we were having issues with this, because if I solve that using the square root method, I get x squared equals -1, right? Square root method says x equals then square root of -1. Well, that's mathematically not something we can do, because if we go by what a square root is, it's a symbol for a number that multiplied 2 times to get the radicand, right? Well, what 2 numbers can I multiply together to get -1 that are the same? Okay, so at the time before I, there was nothing, right? Because any number that was the same had to have the same sign, a positive times a positive, positive, negative times negative is positive, so it was impossible. So he invented I, and he said I was equal to the square root of -1. So then when I take I times I, that's square root of -1 times square root of -1, which is -1. Okay? So that's kind of what his work was all about, and you guys learned a little bit of that in algebra too. I can't remember when he was alive. It was a long time ago. You can Wikipedia that. But like when he was working on this stuff, and this is partially why people, maybe didn't necessarily understand or even think that what he was working on was useful, is because there was no application of I at that point. Okay, human curiosity is one thing that kind of drives mathematics a lot, and drives the discoveries that we make in mathematics. And usually a lot of that stuff isn't trying to address a current problem. Okay, so we talked in the last class, we got a little bit of time here to talk about it, prime numbers. Okay, prime numbers have been something that the human brain has been interested in since we've had numbers. Okay, and we know that prime numbers, they what's our first prime number? 2. Okay, by definition 2, and then we got 3, and then 5, and then 7, and then 11, and then 13, and then 17. And then we got what, 19, 23, 29, 31. So something that we are interested in prime numbers is look at that they come in a lot of times in pairs. Okay, so a lot of times they're either right after each other or like they separate by 2. Even if we go out to, where'd that stuff go? For some reason, this thing jumps me in and out of. So there, and then so we skip 23. There's no pair to go with that, but you see these two are pretty close together. They're a pair, right? So one of the human, if we list like all the first like 100 prime numbers, you're going to see a lot of them being obviously odd numbers. 2 is the only even number prime number. But the other ones, they're always going to be pairs of odd numbers that are back to back a lot. Okay, I forget what the name of what they call them, but it's something that people are interested in. And we have huge servers and data centers and supercomputers set up. Cal Berkeley is one of the universities that is very interested in this. And actually, there are prizes. There are like $1 million prizes for people that are able to find the next prime number. And now, the next prime number, you need probably machinery that costs hundreds of thousands of dollars to process them, because we know prime numbers currently out to like hundreds of millions of decimal or decimal places, okay, or place values, I guess is the word I say. Does that kind of make sense? But why are we interested in? One, people are saying, okay, well, if we can find the next one, then is the next one after that only 2 away? And then we start looking at the gap between these. The first 2 up there, they're only a gap of 2 numbers away. Then 7, 11, they're a gap of 4 numbers away. 13 and 17, gap of 4 numbers away. 19, 23, gap of 4 numbers away. 23, 29, gap of 6 numbers away. But we started out getting larger and larger values. The gaps between prime numbers get very, very, very large. Okay, so I don't know. They found one. I know I read an article last year that they had just found one of the newest prime numbers. But does anybody know what prime numbers are used for the most? Okay, data security. It's called encryption. You guys have heard that before, right? Okay, so what I've got, let's say I've got a bank account, right? Let's just say that my bank account is like that. Okay? Okay, so that's how I access my bank account online. Even when I go to the bank and give them my number and deposit that kind of stuff, they type that in, it gets to James Fay, right? Well, I don't want anybody else to be able to do that. I don't want somebody else banking on my behalf, right? Or I don't even same thing happens with text messages and emails. I don't want to send an email to Anthony and then somebody intercept that, which it happens from time to time. We'll talk about how it happens. And somebody intercept that and know what my communication was with him, right? I want to be guaranteed that when I text Anthony, that it goes straight to his phone and not somebody else can grab it and pull it out, right? Okay. So what happens is that information is coded into numbers. Okay. And then those numbers get multiplied by a very large prime number. The larger the prime number, the better. So I'm just going to write prime here. And that creates a very large, I won't call it a prime number, very large number. Okay? And that very large number is the number that is then, so my device will do this. It will then, over the data lines, send that very large number. Does that make sense? Okay? And that very large number will be picked up by somebody else's device, whether it be the bank or if I'm emailing somebody or texting somebody, it'll be their device. And the way they communicate is that second device will be the only device that knows what that prime number I used in my original device to multiply my account number by. Does that make sense? So how can I take this very large number and get back to that account number? You had to know what that prime number was. And what are you going to do if you know that prime number? You're going to divide by that prime number and out shoots 49347, right? That's encryption, okay? Now, obviously, there's a lot more to it, but that's the nuts and bolts of it. So, how does something, because you hear people, well, I got my identity stolen, I got my bank account number got hacked into, or whatever, right? There are hackers out there that are able to receive, so there's data transmissions happening all around, right? Okay, they're able to receive those or intercept those numbers, those very large numbers that got sent out, and then they have computer programs that will sit and say, okay, let's take that very large number that we just got and just start dividing it by the known prime numbers and see what the results are. And when we get those results, let's plug those results into, this bank's infrastructure or whatever, their software, and see if we get into that person's account, right? And if it works, then they're in. But if it doesn't, then their machine goes to the next prime number and tries the same thing and then says, okay, can I get in? No. Go to the next prime number. Can I get in? No. Keep going, right? Does that make sense? Okay. So if my hacking software, let's say this prime number I chose here was 5, my hacking software would take the 49347 times 5 number, and they would divide it 1 by prime number 2, see if it gets in. No. Prime number 3, see if I get in. No. Prime number 5, see if I get in. Yes. They only had to try 3 iterations to get in, right? Well, the larger the prime number is, the more iterations they have to try, and then that, we get out to 100 million decimal or place values for our prime number. That's going to slow down their hacking software. Does that make sense? And make it very, very difficult to operate. Okay, so that's human nature. But so human nature initially interested in prime numbers. Why are we interested in prime numbers? Just to see how close they are, how big they can get. Okay, are there more out there? Because eventually you're going to start realizing, man, it seems like there are no more. But then the one will pop up. Okay, as we keep going down the number line. Human nature has always been interested in that, and when we first started doing that, centuries ago, millennia ago, there was no computers or application for them, right? But now there's application for them, okay? So a lot of the math that we come across initially, like maybe didn't have any application other than human curiosity. Euler was interested in solving that equation. But does anybody know where imaginary numbers are used the most? But what application? What application? Huh? I'm a little girl? That's not very nice. Have you ever stuck a fork in an electrical outlet? Yeah. I bet. We've seen the repercussions of that. So circuits, okay, resistance and electricity. The way we do the mathematics with them uses complex numbers, use imaginary numbers. Okay, so the way we understand and do the mathematics with electricity to plan like electrical grids and that kind of stuff, and wattage and all that kind of stuff deals heavily with imaginary numbers. So that's an application that electricity wasn't around with Euler. Okay. All right, so let's talk about discriminant real quick. So because you guys had a question, somebody had a question about this, said I got it wrong, had to guess, had to Google, whatever. Discriminant is the part right here, right? That's the radicand in the quadratic formula. If I go greater than 0, what am I saying the discriminant is? What kind of number is it there? Positive. How many solutions is that? 2. That was the first example we did. We had a discriminant that was 37, and we saw then that it had 2 real solutions. Meaning, if we go back to our graphs earlier in the notes, means we crossed the x-axis twice. That's the part that dictates that. B squared minus 4AC equals 0. How many solutions was that? 1. 1 real solution. And then B squared minus 4AC was less than 0 or negative. No real solutions, but it did give me 2 non-reals, right? I mean, it doesn't mean that I don't have something written down. I still have something written down, but they incorporate I, okay? And that's the discriminant. The keyword discriminate means to find differing or altering characteristics, correct? Does that make sense? Okay, and this is the thing that creates that difference. Okay, I don't know how many solutions we have. On Monday, we will start talking about example 2 here, which is path of a projectile. We'll talk about what we call the position function. You guys in physics? Who's in physics? Anybody? Okay. You guys talk about gravity yet? Okay. So there's going to be some stuff that we talk about here that you are going to deal with in some form in physics. Okay, and we'll talk about the different ways. We'll talk about it here, and then the different ways you'll probably talk about it in a physics class. Keep plugging away at that web assignment, and that will be due. I got that